Next up, we have Thomas Holoien from Ohio State University. His field of study is astronomy. His advisor is Christoph Stanek, and he performed his practicum at SLAC. Thank you.
Thanks. Are we on? Hello? Hi. All right, so hi everyone. For the other outgoing fellows wondering why I'm up here, who I am, I'm actually a third-year fellow graduating early, so shout out to my fellow third years. Today I'm going to talk about some of my dissertation work, which is titled Stellar Death in the Nearby Universe, that I did at Ohio State. So since I came to OSU, I have been working on a sky survey project called the All-Sky Automated Survey for SuperNovae, or ASAS-SN for short. And the goal of our survey is to survey the entire sky on as rapid a cadence as possible, down to about 17th magnitude in V-band, trying to find supernovae and other bright transient or variable objects. And just for reference, the ASAS-SN limiting magnitude of 17 is about 25,000 times fainter than the naked eye can see, but this is actually considered quite bright for most professional astronomers, unless you look at planets. And the reason that we focus on this sort of area of parameter space is that no one else is really doing it in professional astronomy, especially supernova surveys. Basically, most supernova surveys tend to go much deeper, which means they're going to find a lot more objects in total because they've got a much larger volume that they're observing in. But they tend to not cover the whole sky. They look at things on slower cadence. And when they do find bright things, it's not the focus of their surveys in general, so they don't get as much follow-up study as the things that we find. So basically, our goal here is to find things that we can observe in great detail with fairly modest resources, which are not as limited as the things you need to follow up much deeper objects. So to do this, we use 14 centimeter lenses. They're actually about this big, pretty small. And small telescopes gives us a wide field of view, so each of our images has about 4.5 degrees to a side. And currently we have 2 units totaling 8 telescopes that are in different parts of the globe. Take about 2,500 images per night on a good night with the weather cooperating with us, and that lets us cover about 16,000 square degrees of sky. At any given time, about 30,000 square degrees are visible, so that means we can cover the whole sky every 2 to 3 days. We have a fully automated data reduction pipeline, and so everything from scheduling observations to downloading the data, processing the data, and to some extent searching for new objects is done automatically. And this is where a lot of the computational challenge comes into play, because we have about 100 gigs of raw data taken every night. That gets multiplied as it gets processed, so we have to find ways to efficiently store and process that data, and then also find ways to automate aspects of the pipeline, particularly how do we find new sources without flooding our inboxes with alerts about false positives. Finally, I just want to mention all our discoveries are announced publicly immediately upon finding them. We're a fairly small team, only about 10, 15 people working on ASAS-SN full-time. So that means we don't have time to follow up everything we find, and we think that the best way to get most science out of what we do is to announce it and let everyone else look at what we find. So just to show you what our units look like, these are 2 pictures of our 8 telescopes here. Our northern unit is called Brutus, after the famous assassin of Caesar and also the Ohio State mascot. It's located in Hawaii. And our southern unit is called Cassius, and it's located in Chile. We actually just got a grant. We're going to be expanding our network with additional units in Texas, China, South Africa, and another one in Chile, which will give us 12 telescopes in each hemisphere. This should allow us to cover the entire sky every night and also give us redundancy in the case of bad weather or mechanical failure at one site. Too far. Okay, so just an idea of what our data look like. This is just one set of images from our Brutus telescope. So you can see we overlap the images just a little bit. That ensures that we don't have any gaps in our coverage. And as I mentioned, our images are about 4.5 degrees to a side. So just for a sense of scale, that's the full moon overlaid on one of our images. So these are very wide fields. And so one of the things that I've worked on a bit is how do we find things in these images? They're obviously very large. There's a lot of sources in them. And we're taking a couple thousand of them every night. So it's just way too much to search by eye. So what we do is we use a technique called image subtraction, which has been used in sky surveys for a while now. And basically the idea here is, I'll demonstrate with a large Magellanic Cloud here, We take a deep reference image that we build by combining many epochs of data. It gives us a nice deep image that makes a nice template for subtraction. We take our new single epoch of data. As you can see, it's a lot fewer of those faint sources that are visible in the reference. And we take these, we align them with each other, we convolve them, and then we subtract them, which gives us something that looks like that. So most of the signal comes out. You're left with a pretty gray image here. And ideally, everything that's light or dark here is something that has gotten brighter or faded in the previous, or from the previous epoch. Now, I say ideally because this is the real world, and actually the vast majority of the signal here is not real. It can be caused by all kinds of things like artifacts from the subtraction process, particularly on bright sources, problems with the detector like hot pixels or cosmic rays hitting it during the observation, issues with alignment, all kinds of things like that. So what we really need to do is find a way to filter out all the false positive signals without tossing out actual things that are in there so that we can drill down and find the real things quickly and not have to spend lots of time on that. So what we do is we cut out a lot of these false positive signals in various ways, and we're actually using machine learning classifier on this now. Basically, we take all the properties of every signal that it finds, things like the shape of the signal, whether it's got similar negative signals nearby, which would imply that it's a bad subtraction, the location with respect to galaxy catalogs, things like that. So we feed all that into a machine learning classifier, and then it spits out a probability that the signal is actually real. And then for the likely ones, it makes an image that looks like this, which we can then go and look at. But basically what we're seeing here is the top three here are one new epoch of data. We always take 3 images at once because it helps us cut down on false positives. And you see all the previous epochs below. This is actually a real signal. It's an asteroid. It's very clearly in all 3 new epochs. It's a nice round source. It's actually kind of near a galaxy. So if this was not matching to a position of a known asteroid, we would probably think that this is a supernova. We would go out and announce that publicly. Oh, bad thing up there. Okay, so that's sort of what I want to talk about with our pipeline. I'm happy to answer more questions about that later, but I want to get into the science a little bit of what we've done with ASAS-SN. So this is just a quick overview slide of a lot of the more interesting and the more interesting things that we found. Basically, we've found thousands of new sources, both in our own galaxy and outside our galaxy, and a lot of these have been followed up with extensive follow-up campaigns, and we've written papers about them. Happy to answer more questions about those later. But the thing I want to focus on, which was a big part of my thesis, is supernovae. So supernovae are basically just the explosive deaths of stars. They are extremely energetic, and they're very important. They produce many of the heavy elements that we know and love. They can regulate star formation in galaxies. They can affect galaxy formation and evolution. And they're also important for cosmology because they're used to measure distances to very distant galaxies. They were a key part of the discovery of the accelerating universe that won the Nobel Prize a few years ago. So we've now found these things are fairly rare. They occur about once every 100 years or so in a large galaxy like the Milky Way. But we've now found as a community tens of thousands of supernovae because of these large sky surveys like ASAS-SN and others. But the key thing to note here is that most of these are found in very distant galaxies. A lot of these other surveys are looking for them to use for cosmology. That means that these are farther away. They can't be studied in as good detail as we can with the things that ASAS-SN finds. So it really creates an opportunity to both study things that ASAS-SN finds in great detail and also to perform population studies of nearby supernovae that haven't been done before. So what I just want to cover at the end here is what I've been working on the last year or so, which is to build a large sample of bright nearby supernovae, both discovered by ASAS-SN and not, so that we can use those to do these population studies that I'm talking about. So basically, we collected data on all bright, spectroscopically confirmed supernovae, bright being magnitude of 17 or brighter, so that it matches ASAS-SN. We took all those between May 1st, 2014 and the end of 2016. That gives us 668 total supernovae. That number is now over 800 if you count ones that have been found this year. We also note whether these things were discovered by ASAS-SN, by other professional surveys, or by amateur astronomers who actually still provide our largest competition for bright supernova discoveries. And we noted whether ASAS-SN independently recovered these in our data or not. This just lets us look at the impact that ASAS-SN is having on the field. We also look at properties of the hosts, like magnitudes and distances, just so that we can look at the environments of these things as well. So just to cover a couple of the trends that we see, this histogram shows the number of supernovae discovered every month from 2012 to 2016. Red here are ASAS EN discoveries. Yellow are the discoveries that were found by other people but recovered independently in our data. And blue are the ones that we do not recover, which prior to June of 2013, we didn't exist, so we don't recover any of those. The dashed line here shows the median value of number of supernovae discovered, bright supernovae discovered per month from 2010 to 2012. So as you can see, after ASAS-SN went operational in the southern hemisphere, every month after that, the total number of discoveries has been at or above the median from those previous years. And ASAS-SN has found or recovered at least half, and many times much more than half, of the bright supernovae in every month. The other thing to note is that the median value of discoveries has increased from 11 per month to over 20 per month. So this is telling us that basically ASAS-SN can and is finding most bright supernovae out there, and that we are finding things that are not being found by anybody else. Our sample is also less biased than the ones that are being produced by other surveys. So this plot here basically shows host galaxy luminosity on the x-axis with more luminous ones on the right because astronomers use backward scales. And on the y-axis, it's showing the separation of the supernova from the nucleus of the host galaxy. The red sample is ASAS-SN discoveries, blue is other professionals, and black are amateur discoveries. So the two key takeaways here, these lines are the medians. Basically, the amateurs tend to find supernovae in more luminous galaxies than professional astronomers. This is not particularly surprising. A lot of them focus on large luminous galaxies that are very nearby when they're looking for supernovae. So they tend to sort of fall in this upper right quadrant. The other takeaway is that ASAS-SN really stands out in terms of the median separation of the supernovae it's discovering in comparison to the nucleus of the host. So basically, we're less biased against finding things near the nucleus of the host galaxy. And in fact, the ASAS-SN median value here is smaller than an ASAS-SN pixel size. So basically, we are finding things that are coincident with the nuclei of their galaxies. This trend also continues in, if you look at it in physical units, kiloparsecs versus angular separation. And finally, I just want to address the completeness of our sample a little bit. So this shows just a cumulative histogram of supernovae by peak magnitude. Red is just the ASAS-SN sample, blue is the ones that ASAS-SN discovers or recovers, and then black is the total sample. This green dash, or the pink dash line, which is mostly covered by the green dash line, shows an expectation of number of supernovae discovered in a Euclidean universe, and the green dash line shows a Euclidean universe up to a certain break magnitude and then a flatter power law. This has not been, the absolute normalization here has not been addressed. This is just normalized to our total sample here, so we can't use this to determine our detection efficiency exactly. But basically, if we just take this naive expectation of Euclidean numbers, we're complete out to a magnitude of about 16.3. And we're finding about 70% of all supernovae brighter than 17th magnitude. So this is a pretty complete sample, should be fairly representative of supernovae in the nearby universe. So just to cover some takeaways here, ASAS-SN is really finding the best and brightest transients out there. There are lots of other ones besides supernovae that I didn't have time to talk about today. But this lets us study them in great detail because we can easily follow them up with 1 or 2 meter telescopes. We don't need 8 or 10 meter telescopes to get follow-up data on these things. And we can also do these new population studies that we've been building these catalogs to do. We are the dominant source of bright supernovae. We're finding supernovae that wouldn't be found otherwise, and our sample is less biased against host galaxy selection effects and less biased against nuclear sources than other samples out there. And our sample is complete to about 16.3 magnitude. So this should allow us to do more complete, more accurate rate calculations and better population studies. And as we expand in the next couple of years, we're going to be dealing with a lot more data, so the computational challenges will increase. In particular, we're going to actually have data coming in at all hours of every day. So the sun will never rise on ASAS-SN. But once we solve those, we're hoping that we'll be able to find more things, we'll find them earlier, and we'll be able to study them longer, and this will make ASAS-SN even more useful than it already is. So thank you. In particular, thank you to the CSGF for giving me this opportunity. It's really been a great few years. Happy to take questions.